Okay, why don't we go ahead and get started? So a few things to do tonight. First of all, let's talk just a little bit about getting back on track. I do want to apologize for the disruption that we've had in the last couple of weeks. As you know, I've had some health issues. I think we'll be back on track okay now, and Andy Catlin is now involved as well to help out, so that if I have any more disruptions, we can minimize the impact on the course. So he'll be helping out, and we'll be moving forward from now, picking up where we left off. I also want to say a little bit about how I'm going to structure deadlines for future assignments. I'm going to make one small change to the deadlines, to how we work those. And then I want to talk a little bit about meetup presentations so that you guys don't just have to listen to my voice every time we get together. And then I want to spend a little bit of time talking about likelihood, which is what we're using in the design solution for the current assignment. And then at the end of that, I'll take any questions you might have on the assignment, on perceptrons or anything else. And also, so you know, assignment 3 will be released tomorrow. I'm tidying up the data, and I'll have that out to you tomorrow. It's got two parts. One is to build a naive Bayes classification model, and the other one is to build a nearest neighbors classification model. Those are both covered in detail in Chapter 3 of the data mining textbook that we have. We'll have some hands-on labs in R as well that you can do, so that you can learn how to write the code that builds these models. And then you'll be asked, for the first time this semester, you'll be asked to implement these models not just in R itself, but in Azure Machine Learning, just to try it out. And you'll actually use your R code right within Azure Machine Learning. So that'll be part of the hands-on lab and not part of the assignment. Okay, so there will be more on that tomorrow once I release that. The new deadline structure, we're going to just have a two-deadline structure for each assignment. I'm going to have a soft deadline, which will be the recommended deadline to stay on pace for the course, so that you can move on to the new material once you meet that soft deadline. And then we'll have a hard deadline that's a little bit later. That way you can have a little bit of leeway for getting extra help if you need extra help, or if things come up, as I know, obviously in my life things come up. That's going to be how we'll handle that going forward. So for example, for assignment 2, you've probably seen this already. The hard deadline is next Monday, end of day. The soft deadline is next Monday, end of day, but then the hard deadline will be the following Monday. And then after the hard deadline, I'll post sample solutions and you can compare with mine. As always, we want this to be collaborative, so you don't need to wait for the sample solutions after the hard deadline. You know, you can discuss the stuff with each other and with me. But at that point, you know, that's the cutoff for getting credit. Any questions on assignment deadlines or procedural matters? Okay. In that case, I do also want to start having you guys do some presenting each week. It can be anything you want to present that's relevant for the course. So it can be a clever solution that you've found to one of the tasks in a lab or in an assignment. It can be something that you think is interesting and relevant for the material that we're studying that's not part of the assignments or labs. Or even if you want to put together a start on a question that you're trying to answer and present that so that we can all weigh in, that would also be perfectly fine. It's pretty loose, pretty open-ended what you want to present. If you go into the course, you'll see on the left side menu that there's a link for Meetup 3 presentation sign-up. That's actually a group that you can join, and it'll take up to 3 people. So I don't want to have more than 3 people present each week, just so that we don't run over too much on time, since you, at least a lot of you, have another class after this one. But we should have time for 3. So the first 3 people to sign up get it. And we'll do that at each meetup. So you'll see another link appear for each meetup as we go. And just to show you in the course what that looks like, I'll show you that in the course here. Let me just exit out of PowerPoint for a second. So if you go into the course, again, you'll see over here on the left-hand menu, there's a Meetup 3 presentation sign-up link. You click there and it'll say join the group, and you click on that and it puts you in the group. Once you join that group as a presenter, just put something in the discussion forum to let us know what you plan to present, or at least a sketch of what you plan to present, so that we don't have two people presenting the same thing. And just check whatever else is there to make sure you don't already have somebody presenting what you might want to present. If there is somebody already presenting what you might want to present, maybe you can work together. That would be fine too. Okay. Any questions on presenting and how to sign up? Okay. Do feel free to interrupt as you have questions. Okay, so what I wanted to do tonight is talk a little bit about likelihood. It's the tool that we're using in our design solution in the assignment number 2. It may not feel like it's the tool that we're using, and you'll see why what we're doing is a simplified version. But let's talk a little bit about likelihood. So the idea that behind it is that we're using a version of Bayes' theorem, except we're replacing some of the probability calculations with likelihood calculations instead, which is to say that because we're using continuous distributions, the functions that come with those continuous distributions don't output probabilities, right? They output the height of the curve, but that's not a probability. So in continuous distributions, you get probabilities through evaluating over regions, and we're looking at specific values. But we can treat them similarly. There's a lot of theory behind this that we're not going to worry about. We're going to use the tool as given. And so let's just take a look at what we're doing here. The idea here is that we have some model theta, and in our case that's either whether it's a dime or a cent, right? So theta is the coin, and what we want to do is evaluate what's the probability that we have the particular coin we're interested in given the input values of x that we have, the measurements of the coin. And so this is the formula that we're going to use. And again, you'll recognize it as very similar to the version of Bayes' theorem that you learned in statistics. The idea is very simple. Here's a one-dimensional version. We actually only have 2 distributions in our assignment, right? You can either have a cent or you can have a dime. And so each of those has a curve that's associated with it. It's obviously in multiple dimensions, but for today we'll just look at one dimension. And then the black vertical line right in the middle, just left of the 4, that represents the actual observed value of x. And really what we're doing in our assignment is just asking for that value of x, which curve is higher. And so the one on the left is the one that's higher here, so that would be the one that we choose. Now it's not quite that simple. And we'll look at why we're making it simpler in our assignment. But let's talk a little bit about what we're doing. So we know we have either a dime or a cent. That's one of the assumptions that we're making. We're not worrying about nickels, quarters, Canadian coins, or anything like that at this point. We could make that model. I think at that point we're getting into tedious work that's not really helpful for a learning standpoint. But we're going to assume we have either a dime or a cent. And so we're going to build this probability function for each of the 2. Right? We're going to use the the version for the dime and then the version for the cent. And if you look closely, you'll notice that the denominator is the same for both. And so one of the simplifying assumptions then that we're going to make is that when you program your code, you only have to program the numerator, because that way, since the denominator is the same, when you compare the 2, the numerator is what decides which one's bigger. So the second assumption, I guess it's the first assumption that I've got in my slides that we're going to make, is that it's equally likely that you have a dime or a cent, right? That we have no prior probability that one is more likely than the other. So we're setting those equal each to 0.5. And if you look at the way the algebra shakes out, what we do then is we just say the 0.5 in the numerator cancels with the 0.5 that we can pull out of the denominator, and so we can actually ignore that. If in the real world you wanted to make a certain assumption about the likelihood of each coin, you would want to build that into those probabilities. And there are various ways that that could happen, right? You might just know that pennies are more common than dimes. And so you might assume that the probability that it's a penny is actually 0.7. The probability that it's a dime is only 0.3. Then you wouldn't be able to pull it out quite so neatly. But that's relatively easy math as well. And how you make that assumption is an interesting question, because it might be that there are more pennies in the world, but it might also be really unlikely that anyone's going to shove a penny into your vending machine trying to pass it off as a dime. So you can think about how you might make those different assumptions, but for the assignment we're going to assume they're equally likely. Okay, the distribution that we're using, let me talk a little bit about this distribution. It's the multivariate normal distribution. It's a bell curve in many dimensions. In our assignment, it's of course 3 dimensions. And there are 4 parts that it's important to know what they are. The first is the covariance matrix, or the variance covariance matrix. And we're going to use E for that. A lot of books use sigma, but E is just an easier symbol to use, so I used E. And that, we'll take a look at one here in just a minute, but that gathers together how much variance there is in each of the measures that we're taking, and it also measures how do they covary. So we'll take a look at that in just a minute. The second thing that it's important to know is the means. So in the normal bell curve, in a one-dimensional bell curve, you have a mean. In a multi-dimensional bell curve, you just have a vector of means that correspond to the vector of inputs that you can have. So mu still represents the means, it's just that now it's a vector. You have d is just the number of dimensions, so you take the square root of 2 pi and you raise it to the d power in your fraction on the left there. So d is just a measure of how many dimensions. In our coin task we have 3. And then x is the vector of inputs for a particular coin. So as you're working through each observation, that would be your inputs for the coin. A second simplifying assumption that we're making is that the coin measures follow this distribution. Now, there are various ways we could handle that. We could verify it from the sample data. I actually generated the data randomly using a multivariate normal distribution generator. So if you actually tried to verify that it fit a multinormal, you ought to get a pretty good result there. You might know that it fits a multivariate normal distribution from some authority. In this case, maybe you did some research, you contacted the Treasury Department, talked to someone at a U.S. Mint, and you just know that they follow a multivariate normal distribution. Or even if you don't know it, you could assume it based on some particular knowledge or something that you've seen in the past. But that's an assumption that we're going to make, is that they do in fact follow the multivariate normal distribution. It's not a requirement, but it does make it easier for this assignment. Okay, assumption number 3 is that we're going to assume that the 3 measures, which are the coin thickness, the coin diameter, and the coin mass, are independent of one another. And in the assignment I'm going to ask you to think about that a little bit, because that should give you some pause. But I don't want to deprive you guys of the joy of thinking about that, so I'm going to go ahead and leave that for your assignment. But the way we handle that in our variance covariance matrix is we take these off-diagonal entries. Those are the measures of covariance between the 2 variables, and we make those a 0. If those are zeros, then the variables are all independent, and the diagonal just has the 3 variances. And in the assignment, it gives you the order that the inputs are recorded here. Okay, so that should give you enough to do the assignment, the design part of the assignment. And just as a reminder, when we're talking about learning versus design, the learning approach, we don't know the underlying functions, and so we're trying to approximate them from data. And the design approach, we know the underlying functions, and so we don't need data in order to build our model. We might use data to suggest the parameters of a model, or we might use data to test our assumptions, but we make the assumptions of the underlying functions and then we use those to answer the question. So we don't rely on data to build the actual model. Are there any questions at this point? I'm hoping you guys have all gotten started on this assignment, but I do want to open up tonight mainly for discussion of the assignment and questions you might have. I'm almost a little bit nervous to ask. Has everybody gotten a chance to start the assignment? Anybody having any trouble with anything? Started to look at it. Okay. Yeah, I think it's not a terribly challenging assignment from a programming standpoint. Just make sure you handle your matrix arithmetic correctly and you should be fine, at least for the design part. I did post a link to a video that the book that inspired this assignment. He gave this as an example of the sort of thing you might do. He didn't actually, he didn't have the full assignment in his book, but it gave me the idea. So full credit to him for coming up with the idea. I do encourage you to watch that video. I think it's a really good video, and it focuses pretty heavily on the perceptron, which is what we're using for the learning part of this. So I was very careful to make sure that the training data are linearly separable, which is to say you can divide them with 100% accuracy if you choose the right hyperplane. The testing data may not be that way, and that's okay. So when you're doing the assignment, don't worry if you don't get perfect classification on your testing data. That's okay. I'm not expecting you to take that into account and go back and rebuild your model. So the idea here is to build your model on the training data and then apply that to the testing data and make your predictions. Let me talk just a little bit about that then in the assignment. Let me pull it up here. So you've got you've got 3 data sets that come with this assignment. You've got your training. I think I accidentally introduced a typo there. So you've got a training data set which you should use to build your model, and then you've got a public test data set which has answers in it. So what you would want to do is train your model and then test it on the public data set and see how well it does and comment on that. The second testing data set does not have answers, and that's the one that I'd like you to apply your model to, and we'll see how well you do. You're not going to be graded on whether it's perfect. You're going to be graded on whether your model is correctly applied to the to the test data set. In fact, I don't expect anybody to get 100% perfect answers. The perceptron, if you're curious, is not a commonly used model for classification, and the reason for that is that it requires that the training data be perfectly linearly separable, and that's a really rare thing to have happen. But it is a good first choice for learning how classification works. And you're going to get into 2 much more effective algorithms in the next unit when we talk about naive Bayes and nearest neighbor. Those are actually very commonly used algorithms even today, even though they're both very simple, and naive Bayes in particular makes an assumption of independence very similar to the one we're making that's probably not true. And yet, even though it makes that assumption, it tends to work very well in certain situations. If you have a spam filter, for instance, on your email, it's almost certainly using a naive Bayes approach. That's the most common approach these days. Okay. And again, I love when you guys find R packages that do these things, and it certainly is fine if you go out and find some. But I do also want you to code these things in hand so you get some experience with that. Are there any questions? I feel like I'm doing a lot of talking and you guys aren't. All right, so it looks like you guys are noticing there are even more videos for the Caltech course. Yeah, Yeah, and I actually do highly recommend it. I think I almost used his book for the course. I really was tempted. But I'll just pull up his website here for his online course. So you can see here he's got a lot of lectures, and each lecture has a video that accompanies it, as well as some questions and answers and slides. There's a lot there, and we're gonna use some of it. We're gonna look at some of the things that he does in this book. The math was a little bit higher than I wanted it to be in the book. Not that I don't think you guys could handle it, but it wasn't where I wanted to focus. So even though he talks about it being a very practical book, it's really not as practical as I was hoping. And there are a lot of basic things that he glosses over. So I would certainly encourage you, if you have time, money, and inclination to do so, to pick up a copy of the book, Learning from Data. But it's supplementary, right? So a lot of his lectures are very good and useful. I would encourage you, in fact, I will post it at some point, to go to and watch the training versus testing lecture. That's a pretty good lecture as well. Okay, the other thing that I wanted to do then tonight is just take a quick peek at Azure Machine Learning and show you how to build an experiment so that you can run things in it. As I said, I'm going to have labs where you're asked to do that next week in the naive Bayes and nearest neighbor algorithms. But you could also, if you want to, you could build these perceptron and multivariate normal solutions right into Azure Machine Learning as well. So has everybody had a chance to go and take a look at Azure Machine Learning? Anybody not able to figure it out yet? Yes, Brett, I know you have. Anyone else had a chance to go? Okay, so the website, I'll put it in the chat window if you guys want to bookmark it. You can go to, oops, you can go to studio.azureml.net, and you'll see here a Get Started Now link. And there is a free trial use of it. We had actually gotten permission to use it for the course, but as long as you stay under certain limits that this course will certainly stay under, there shouldn't be any charges for you to use it. In fact, you don't even have to sign up for credit card or Azure subscription. So if you accidentally do a cross join and create a massive data set, you should be protected. I think it'll just error out and won't let you do it. And then if we need more capability than what's available from the free trial, we do have permission to use an account, I believe, with $100 credit a month. And to put that in perspective, in December I used it almost every work day, almost the entire day, and I think my bill at the end of the month was $8. So we're not looking at massive costs here. What really drives the cost is when you start getting into the really big data sets, because Azure charges for storage and for compute time. And so the small data sets that we're working with are pretty easy and cheap to work with. Once you've signed up, you can sign into your studio. And you'll see something that looks like this. You can go to the home page and you can find all sorts of learning resources here as well. They're literally changing these daily. In fact, there are now in Azure Machine Learning, there are now some new features that I haven't even looked at yet that I noticed came on today. So if we start a new experiment, start a blank experiment, this is where you do your work. And what I would encourage you to do would be to upload the coin dataset, the training dataset, and the test dataset, and then you can actually work with them in here. So I'll have more material for you in the lab, step-by-step instructions to do things in the lab, so that you have a chance to play with this, because I think this is a really neat tool. I'm not 100% Microsoft all the time. Maybe Aaron Palumbo is, I think, but other than Aaron, none of us have to become Microsoft experts, but I think they right now have the leading data mining tool in the industry. I think with this tool they surpassed all the others I've seen. So I think it's good to get some exposure to this. In coming weeks too, you'll have a chance to implement some of these things in things like MATLAB and Python as well. So play with this as well and get a feel for this. I think this is a really fun tool. But just so you know, the way you'll typically do things is you'll bring your data set in. So I'll just pick a data set at random here. I'm not going to save this experiment. But let's say I've uploaded my coin data. I don't think I have in this workspace. So pick a data set, the one that you upload, and then what you'll want to do is use an execute R script. So you'll see, and wow. Okay, so earlier today apparently, or recently, they enabled Python as well. So you can even use Python now. But you bring a script module onto the page, you would connect your data set to the script module, and then you can actually copy and paste your code right out of RStudio or R and paste it into this window. Just take note, the way that it learns what the data sets are that you're bringing in is by assigning them through these first couple of lines of code. So dataset 1 will be the dataset that I just attached to the module here. So I can refer to this iris2 class data as dataset 1 in my code. And then to output code, you use these last couple of lines right here. And then you can access that by pulling it from the dots on the bottom of the module. So there'll be more on this in the lab, but that's really all you'll need to do in order to run the things that we're running for this assignment. And then for the naive Bayes and nearest neighbor, as I said, those are two of the simpler techniques. And so if we go back out to the list of pre-created modules here, and we look under machine learning classification modules, so initialize a model classification, we'll actually see that they don't have both of those in here. Because they're two of the simpler algorithms and not necessarily two of the best algorithms, but you can code them through R. So anything you can do in R, you can do in here. We will take a look at some of these other algorithms as we go, so you'll get a chance to use the out-of-the-box algorithms as well. Any questions at this point? Yes, Brian, I am recording this, and I'll post it. Yeah, I think this will be fun. I think this is a group that probably likes to code things by hand a fair bit, so you'll get the chance to do that. But obviously, this drag and drop environment is also a really good one. The most advanced thing I have done with Azure, I can't show you because it's client work that's not free to show you, but I did build I pulled some data from Hadoop, some sales data, and I used it to generate the demand data for sales at each store, and then we built a forecasting model based on that. And the idea then was that my forecast for each store for each item was passed out into a Power Pivot model, and some visualizations were created for the executives at the company. So that's probably the most advanced thing I've done with Azure. It was a little bit of Hadoop, a little bit of Azure Machine Learning, and a little bit of R, and then some people did some fancy visualizations that aren't my area, so I passed off my stuff to them. But I was able to pass the stuff off to them because of some of the capabilities here of Azure Machine Learning. In particular, you can create workspaces, and so you'll see I have 3 workspaces here, and this BTE 2014 is actually the one that contains that that task. So. And then we can invite people to those workspaces. So as you're using this, one thing you might consider is inviting your group members to your workspace or to one of your workspaces so that you can collaborate on the project that way. One of you can start building it, another person can come in and check details or try something different, duplicate the experiment, and you can actually work collaboratively in this environment. That's one of the really nice parts of this tool, is the ability to collaborate. The other one is the ability to deploy it using a web service. That's a pretty powerful thing as well, so that people could send their data and get the result back without having to come in and mess with your model. Let's see, there was another question here. Let me see. It was about the labs, I think. Will there be lab material specific to Azure? Yes, there will. I'll put some of that out next week for the next assignment so that you guys are able to build them in here. The first labs in Azure will be very simple. As I said, you really only need about 2 modules to execute what you need to execute. And then as we go through the semester, we'll build on that, and we'll learn a little bit more. I do want to remind you, of course, that Azure Machine Learning is one of 3 options, and you're required to use and demonstrate some proficiency with 2 of them. So if you really, despite my enthusiasm for the tool, if you really don't like it, you can opt to use the other 2. But I would encourage this tool. I think it's a game changer. I think Microsoft has come out with something really powerful here. So let's see. Other questions? How does the speed compare? I don't know. The models that I actually built, I built on my personal machine first, which is nothing special. It's it's a reasonably fast personal computer, but the Azure code, when I ran the same code in Azure, it did run faster. So I'm not sure I could quantify it at that point. But they do automate the multiple processors and handling massive data sets for you. You don't even have to worry about that. There probably is the ability to run the code faster if you can optimize yourself, but that's not my area. How do I decide which one to use? That depends on the client. And in particular, the very first question we're learning that we need to ask is, I'll put the URL in there again. The very first question we're learning to ask is, do you feel comfortable having your data on the cloud? Because it is entirely a cloud-based tool. So some of the bigger companies that we're working with are still terrified of putting their data on the cloud. I have a meeting scheduled with one of the team members that's actually working on the project, and every time I talk to him, I ask him, are you guys ever planning to release a version that can be created locally? And so far the answer is no. But Microsoft also did just acquire Revolution Analytics, so who knows where they're going at this point. They're embracing these tools pretty heavily. And actually, Brian, to elaborate on that even a little bit more, you can use Python and R and still use Azure ML, right? So R has been in there for a year, and Python's pretty new, but yeah. So it's not necessarily even an either or. Other questions? Somebody's got to ask something, so I know you have voices.
I guess I might. I was wondering about the complexity of things you can do in Azure. Like, I don't know. I guess I've got Bayes models on the brain at the moment, but like, loopy belief type things, or natural language processing, where you get some complex relationships in there. Does that support this kind of thing, or is it?
Yeah, it does, and they're actually the natural language processing stuff is not particularly developed yet, but it is coming. They have a little bit of text analytics capabilities right now, but not a ton. But they're working on it. This just went to general release, I think, last week. It's been in public preview, so you could sign up and play with it, but it's still actively being developed. So there's still a lot that's coming out. Of course, anything you can do in Python and R now you can do here. So it supports just about anything you might want to do that way. But yeah, so I don't know if that really answers your question, but you can build some pretty complicated experiments, and it's got some pretty powerful algorithms.
Are there limits to what you can run in R or Python?
What kind of limits do you mean?
I mean, like in Python, you can import pretty much anything you want.
Okay. Yeah. So I honestly just learned when we opened this right now that they have Python in there now. But let's see. So there's what's called a script bundle. I knew they have it for R, and it looks like they do have it for Python, where you can upload packages, you can upload scripts of your own, and then you'll have access to them. So in R, you bring in packages. I think they're last I checked, they were well over 300 R packages that were already pre-installed. And so if there's one that's not pre-installed, you can upload it through the script bundle. So in theory, there should be no limitations. You should be able to bring in whatever code you want, whatever tools you want. Okay, so we're focusing in this first real quantitative assignment on really learning the difference between learning and design and the two approaches. So I want you to keep that in mind as we go. This course will be focusing on the learning side of it, right? Machine learning, and we will have some courses. We'll have some opportunities to look at corresponding design approaches. The likelihood approach is actually very similar to what we do with the naive Bayes algorithm. The difference between the two is that in our likelihood approach here, we're going to be using a predetermined function, right, the multivariate normal function, whereas in naive Bayes, we're going to determine the probabilities from sample data. So the concept is very similar. But again, learning comes from data, design comes from underlying functions that we believe we know. So keep that distinction in mind as we go throughout the semester. And please do let me know if you have questions on that.
So Mike, are you saying that naive Bayes is learning? Or is this is more of a design?
It is a learning algorithm. So it is a machine learning technique. But it comes to very similar a very similar structure to this. Let me pull this back up. So the design approach that we're using here is based on functions that we're assuming are true, right? In naive Bayes, you're going to calculate these probabilities from training data, and then you're going to use a very similar approach. It's not identical, it's just very similar. So the key distinction between the two, again, is going to be that one of them is based on probabilities learned from sample data, and one of them is based on probabilities that are assumed to be true from functions underlying the model. And then nearest neighbor is just completely different, right? Nearest neighbor, as you'll see, is basically it's as simple as we look at the 5 observations closest to it, and we assign the value that's most common in those 5 observations. Right? It's literally just look at the nearest neighbors and see what they say. But it actually works remarkably well.
So So I guess in naive Bayes, you are making a lot of strong independence assumptions
We
between
do.
all the
We
all
do.
the
We
variables, right?
we assume that they are independent, and the reason we do that is because if you don't, you end up with a situation where you might have a value that's possible for one of your variables that never occurs, and then you would assign it probability of 0, and we don't ever want to assign a probability of 0. And so if we assume that each of the variables is independent, we'll never run the risk of having a grouping that's got a 0 support data set behind it. Let me, I don't know if that was clear. Let me see if I can show you what I mean. So imagine we had something like this, where, let me give a table, and you've got sunny weather. I think this is similar to an example that's in the book. You've got sunny, cool, Monday, and then you've got go golfing. So the question is whether you go golfing or not. You got sunny, warm, Tuesday, go golfing, right? And so on, right? So you have all these observations that measure each of the 3 inputs and then give the answer, go golfing or don't go golfing. But you could end up with something that never occurs in your data. So for instance, imagine rainy, cool, Friday. Suppose there's not a single observation in your data that's rainy, cool, and Friday. How do you make a prediction at that point? There's no sample data to support your prediction. So what we do is we assume independence of the 3 columns of inputs, and we say, okay, well, what's the probability of golfing if it's raining? What's the probability of golfing if it's cool? And what's the probability of golfing if it's Friday? And we combine those after we look at those values. We combine them and make a final prediction. So by assuming it's independent, we reduce the chances of having an input set that doesn't occur in the sample. Right? We don't have to worry as much about out-of-sample predictions. So we do assume independence of the 3 columns, even if they might not be. Does that make sense, Aaron? Is that?
I think so. I guess, I don't know. I guess that there's still an element of design in that then, right? Because you're letting the data kind of tell you some things, but you're not letting the data tell you that these things are interdependent.
That is correct. Yeah. You're imposing that assumption of independence on the data. So it is an aspect of the model. But really, again, because it originates from the data and not from an underlying probability model, a design solution might go something like, we know what days of the week the guy works, so we know there are certain days of the week where the probability that he goes golfing is he only gets 4 weeks of vacation a year, so the probability he goes golfing on a Monday, it's 4 out of 52, for instance. Of course, that assumes he golfs every day he's not at work. But that would be more of a design solution, right, where we're imposing a probabilistic model on the problem without having underlying data support it. But don't get up, again, don't get too caught up in learning versus design. There are aspects that apply to both, and there's some overlap, as we'll see. But remember, everything we're doing this semester we're going to try and do where we're approximating the truth using data. This imposes a strong assumption. We won't always impose strong assumptions, so other methods will not make the same assumptions. The disadvantage of those other methods is that they're more complicated. Often the advantage is that they work better. But not always. Naive Bayes works really well, again, for things like spam filters. And the Titanic. It works okay for Titanic data, predicting who died and who lived, which is one of the labs.
Is that a Kaggle competition?
It's one of their training ones. Yeah, they have a learning opportunity there. We'll mirror that a little bit in that we'll use the full data set, and I don't think they make the full data set available, right, because they hold some of it back for scoring your predictions. It's been months since I actually looked at their training on the Titanic one, but I think you upload your predictions and they score it without telling you which ones were wrong. So, Brett, okay, good. Well, so you're the expert. You can help everyone else out. And I'll have a few different ones you can do. It's not going to all be the Titanic one. That's just one of the ones that'll be available. The book that we required that's available free as a PDF, right? Let me just bring that up. All right. So this book here actually has each chapter has labs, and so if you want more practice, you can go to this book and find things that where it asks you in their lab sections in each chapter to implement the different models. So I'll have examples that you can follow, and then this gives you more examples. Your books give you even more examples. So don't hesitate to try playing with some of these different things. What else? We got about 10 more minutes if we want it.
We'll be talking about cross-validation techniques.
Yes, we absolutely will. I think we're going to get our feet wet with some of the algorithms first, and then so we'll start out with the training and testing data sets. You build your model on the training data set, and then you test it on a testing data set. So we'll keep it simple at first and just do that. And then we'll talk about some of the limitations of that. For instance, one of the things that's commonly done that's actually mistaken is always using the same testing data set. You generally, every time you test your model, you want to, if possible, you want to test it on a different testing data set. Because otherwise it becomes a game of build your models in the various algorithms you have available, test them on the testing data set, and use the one that performs the best on that testing data set. But then you run the risk that you're performing very well for a particular subset of data and not necessarily for the whole population. So you don't want to over-rely on just one testing data set. So then you get into, well, do I have enough data to create enough different testing data sets? Or I was trying not to use the word overfitting yet since we haven't talked about it. But, and then you also get into techniques like cross-validation, which also try to eliminate overfitting. So yeah, we will get into that, definitely. And we'll get into it even more in the second and third courses. Overfitting shall become our nemesis. It's the thing that'll be the most dangerous about this stuff, that we run the risk of finding patterns that aren't actually there. So. All right. Last chance for questions, procedural, material, any kind of questions you might have. Okay, so again, I apologize for the disruption that happened. We're taking steps to make sure that even if I do need to step away again for a little bit, the course will proceed as planned. So you can thank Andy Catlin. He's going to step in and help with that. And I think I'll give you back these last 8 minutes, and you can go. I think most of you are actually also in the quantitative finance class, which I believe starts at 7:45. So I'll give you back a few minutes, and you can go get ready for that. And I'll post this recording. I know a couple of people had to come in late. I'll post this recording tonight at some point. It just takes a little bit of time to process the video, and then it'll be up in the meetups folder. And shoot me an email or give me a phone call if you have any other questions or you want to go over anything. Otherwise, have a good night.
Thanks, Mike.
Thank you.
Good night.